Hello. Today we will talk about finite-dimensional norm spaces and about specific features what can be found there. Let us have a normal space. And we know what X is finite dimensional, precisely d-dimensional vector space. It means what we have here d linear independent vectors and do not have d plus 1 linear independent vector. So let's choose any system of d linear independent vectors. We once choose it and fix, will not change. Let's call this system of vectors basis. For each x from X, we can find a d-dimensional vector alpha, such what alpha has these properties, such what X can be represented as a linear combination of xk with parameters alpha, with coefficients alpha. So for each element we can find these actually coordinates in regarding this basis. Let us define a function. We call it norm with index 0 as a sum of absolute values of these coordinates. So for each element of X, we can calculate this function. Indeed, we can uniquely choose these coordinates, and by this formula we calculate this what we call the norm with index 0. In exercises we will prove what this is indeed norm in X. So We will prove it during our meeting on exercises. Before proving additional facts about this norm, we need some definition. Let us have a vector space and two norms defined on this vector space. We say what these norms are equivalent and write this wave if equivalent. We can find two constants. D small and D capital, such what for each element from X, we can estimate second norm by the first one, both from above and from below, like is shown here. Another task for you. Please prove what such properties are fulfilled. Each norm is equivalent to itself. First one. Second, it is called reflexivity. If first norm equivalent to second one, it happens if and only if we have reverse. Second one is equivalent to the first one. So this is fulfilled only if this also is fulfilled. It is called symmetricity property. And last property. If first norm is equivalent to the second and the second is equivalent to the third, then first one is equivalent to the third one. So please prove it. And we will discuss it on exercises when we will discuss this video. Lemma. Actually, the main most complicated claim of this paragraph we have our initial norm in space X, now vector space, and we have built the new one with index 0. And the lemma says what these two norms are equivalent. Let's prove it. We will use several steps. Let's consider vector alpha. D-dimensional as an element of Rd. And let us denote the norm in Rd by just brackets consisting of one stick as absolute value to distinguish it from norm in X. So norm, it is convenient to define norm in Rd like sum of absolute values of coordinates of alpha. Let S is so-called unit sphere in Rd alpha from T such that absolute value of not absolute value, but this norm is equal to 1. Please prove what it is bounded and closed. Bounded means what we can find some ball what contains this set. So yeah, some center some radius. So each set is called bounded if it belongs to some wall. So we have this nice set, and let us consider function defined on alphas for each alpha, and it is calculated from this formula. So we compose this linear combination and calculate the norm of this element in X. So f is a function from Rd to R. It returns real numbers for each element from Rd. Next item, and in this item we will prove small claim: f is continuous in Rd. Proof of this claim. Let's consider two elements, alpha and beta from Rd, and we consider the absolute value of difference of these values, function on these two elements. It is equal to absolute value of difference of two norms. For norms, we know the inverse triangle inequality, what says what absolute value of difference of norm is smaller or equal than norm of the difference. Difference we will represent here is the norm of difference. Then we express it in more convenient form. Next, we use ordinary triangle inequality. I continue here. We can move constant out of the norm, it will obtain absolute value. So we can change it like this. Let us define a constant C as a maximum of all norms of basic elements. We have finite numbers of these basic elements, so it will be also finite. And we can write finally sum of absolute values of different, and this is exactly the norm we used in RD. So we have proved what such inequality takes place. Actually, it is more than just continuity. It's called Lipschitz continuity of function. It's nearly differentiability. But if we consider, if we like to prove it, we can do it easily. Consider a sequence that converges to alpha, then put in here alpha n instead of beta, we can write convergence means what it is. This term goes to 0 when n goes to infinity, and that's it. So our function of alpha n converges to f from alpha for each alpha n what converges to alpha. So this exactly means the continuity of functions. Okay. So f is continuous. S is closed and bounded. And in RD we have Weierstrass theorem. Very important fact from mathematical analysis, saying what each continuous function on closed and bounded set is in RD, R or RD not in infinite dimensional space. This function reaches its maximum and minimum values, so it is bounded. So f from alpha so we can find two non-negative values. Non-negative because function f is non-negative, it is norm. Such what function of each element from S lies between small and capital D. Next item, and once again claim. Small d is positive. So, proof of this claim. Let's assume what d is equal to 0. We can find an element in S according to the Weierstrass theorem such what f from this alpha 0 is equal to d, so it is 0. It means what to 0. So this is function f, so it's equal to 0, but it is norm in x, so element itself is 0. Basic vectors are linear independent, so the only option we have is all coefficients need to be equal to 0. So from first to last. And if all coefficients are 0, it means what sum of absolute values is equal to 0. But alpha 0 belongs to S, so this sum of absolute values equal to norm of alpha 0, and for all elements in S it needs to be equal to 1. So we have contradiction, and our assumption that d is 0 is wrong. Item number 5. We have proved what f from alpha is between small and capital D, and small d is also positive for each alpha from S. Let's try to reformulate it not in terms of alpha, but in terms of initial variables x from initial space. F is equal to alpha 1 x1 plus alpha 2 x2 and so on until alpha d plus xt. Here it is element x, so here we have norm of x. So instead of this, we can write what norm of x is between d small and d capital for all. Next, let's consider this part. Alpha belongs to S means what norm of alpha is equal to 1. But norm of alpha is sum of absolute values of coefficients. And it is exactly equal to 0 norm of x. So the right part of this formula can be formulated like this: for each x from x, such what zero norm of this element is 1. So this and this are equivalent as this line and this one. So finally we have proved this nice formula, and we need just one more small step in order to finish our proof. Let's take x from x, any elements. Only one requirement, it is not 0. So for x equal to 0, everything is obvious. So let us denote x with a roof as x divided to its 0 norm. When obviously 0 norm of this new element will be equal to 1. Then for this element we can write this inequality. Let's go back to initial x. X with roof is defined as a ratio between x and normalized X. So for initial element we can write this, and finally once again, we have proved it for non-zero elements, but for zero elements it is also true because all terms obtains value of 0. So we have done it. And actually trivial consequence of this lemma is most important fact from all this paragraph. Theorem. Let's X is vector space, finite dimensional. If we have any two norms in X, these norms should be equivalent. Please try to prove this theorem yourself using lemma. We will discuss it during our meeting, and I need to say what equivalence of norm means. Equivalence of convergence. So if sequence converge in one norm, it also converge in the other equivalent norm to the same limit. It means equivalence of such things as openness of set, closeness of set, properties of norm space like separability, like completeness, everything. So this theorem says what it doesn't matter what norm is defined in finite dimensional space, all properties of the space will be the same. So you can take whatever you like just to satisfy axioms of norm. Very useful fact. Another important definition. Let us have two vector spaces. X, Y are vector spaces. These spaces are called isomorphic, and we write the same symbol as for norm, and isomorphic vector spaces. If we can establish one-to-one correspondence between elements of x and y. So each element in x has a unique correspondent in y, and each element in y also has a unique correspondent in x. And this one-to-one correspondence preserves the linear operation. So if x corresponds to y, then let us write like this. x1 corresponds to a1, x2 corresponds to y2, then alpha 1 x1 plus alpha 2 x2 should correspond to the same linear combination of y. So in this case, two spaces are called isomorphic. Or we can show very simple examples. For example, space of three-dimensional vectors A are free, so elements x1, x. And another space is symmetric matrices of 2 by 2 dimension. Matrices with elements on minor diagonal equal to each other. Obviously, there is a one-to-one correspondence between R3 and this space of symmetric matrices, because each matrix is defined by three elements, and the same for a vector. And easily it can be proved that this correspondence preserves linear operations. So, if we continue with this definition, if we now consider not vector but norm spaces, we say what x and y are isometrically isomorphic, and write the same wave if vector space x and y are isomorphic, so all requirements given here are fulfilled, and one additional requirement: if x corresponds to y, then norms of x in x should be equal to norm of y in space y. So norm of x this space, norm of y in this space. And the theorem what also follows from our first lemma. Let's x is normal space, finite dimensional, if dimension equal to d, then x is isomorphic to Rd as a vector space, and we can choose a norm in Rd in such a way to make these spaces isometrically isomorphic. So we can find a norm in Rd in such a way what x with norm x we can build a norm here in Rd, and we know what in Rd all norms are equivalent because it's also finite dimensional, to make these spaces isometrically isomorphic. And also I must add what if spaces are isometrically isomorphic, also all properties are the same, and it can be built, and we will can be proved sorry, and we will do it on the exercises. From this theorem it follows what each finite dimensional space in particular it's complete and also is separable. We will prove it in exercises. And I think it's all what I wanted to say. Thank you, goodbye.